Now, chromatography is something that we're most likely very used to, right? For chemistry, right? So we're used to paper chromatography, just putting those pigments, right? For example, all of us would have done the experiment of crushing, mulling. It's actually called mulling, right? Leaves, boiled leaves in biology or anything like that, and then putting the chlorophyll mixtures, right, on the specific lines and actually separating the mixtures, right, into their xanthophylls and carotenoids, right? So you guys would have done experiments like that before. If not, you did it with like pen inks, right, or something like that, right? So it's the same type of process that we're looking at for chromatography, but we're actually just looking at the deeper chemical underpinnings of the entire separatory method, right? So our general objectives, we must be able to explain the theoretical principles upon which chromatographic methods are based. We must be able to explain the terms retention factor, retention time, visualizing agent, and the solvent front. We must be able to describe the basic steps involved in separating and quantifying the components of a mixture. Name examples of commonly used stationary phases rather, and carry out simple experiments to separate the components of mixtures using paper column and thin layer chromatographic techniques. In this PowerPoint as well, I put in gas liquid chromatography GLCs as well, right? Just have a look at that. All right. So it's just some extra information there. Let me just have a look at the syllabus before I start. Mm, Pigments. All right. All right. All right. All right. So syllabus checks out. So let us begin. So please note, in paper and thin layer chromatography, right, the components of the mixtures are identified by their retardation or retention factor values, right? The R value is the distance moved by a specific component from the baseline divided by the distance moved by the solvent from the baseline. Interesting. The visualizing agent, right, is similar to something that we see in UV. They're colorants. Visualizing agents, right, react with colorless compounds to give us that bathychromic shift that we spoke about in UV, right? That shifts into the visible light, right? Or with thin layer chromatography to give separated components, right? If not, we actually put them under a UV machine in order to scan them with UV light to see, right? In gas chromatography, the components are identified by retention times, right? Let's have a look at this now. The principles of chromatography. We know it's a technique that is used to separate components of a mixture, right? And in chemistry, a component is one component or element in a mixture, right? So we're looking at the fact that we can separate these two things fundamentally, right? It works by dividing the components based on, well, between these two different phases, right? So this is called partitioning, right? So we're working via partitioning, right? So for example, water and hexane do not mix. They form two different layers, right? When we shake an aqueous solution of iodine with hexane, most of the iodine goes into the hexane layer, but some remains in the aqueous layer. We say that the iodine is partitioned between the two layers. And we spoke about that a little bit just before, right? In separating techniques. All right, partitioning and the partition coefficient. All right. But we're not going to be really using partition coefficients for chromatography. All right. So the principles generally know. The mixture is separated. The mixture to be separated is dissolved in a fluid, and this is called our mobile phase, which carries it through a structure holding another material called our stationary phase. All right. The various constituents of the mixture travel at different speeds, causing them to separate, right? And this is based on differential partitioning between the mobile and stationary phase. So subtle differences in the partition coefficient result in different differential retention on the stationary phase, and thus affects the separation, right? So based on their molecular structure and etc., right? Some are going to be moving faster than some, and the retention is going to be different from some other substances, and that's how you get to separate them, as you can see here on the diagram over here, right? This is in a diagram of column chromatography, right? Really, really simple, right? You're gonna be moving the mobile phase to the stationary phase, and after a while, we can see different types of interactions, right? As the green dots interact with the stationary phase, and the blue dots remain in the mobile phase, and you can see that they're separated like this after. All right. So chromatography may be um, preparative or analytical, right? So the purpose of preparative chromatography is to separate the components of a mixture for later use and is therefore a form of purification, right? So it's used for purifying stuff, okay? So we have that there. So the chromatographic terminology that we need to understand is retention factor will be the first one, right? This is defined as the ratio of the distance traveled by the solute to the distance traveled by the solvent, right? So where are the actual things present on the thing versus the solvent front? The visualizing or locating agent right now, these are solutions that are applied or sprayed onto the finished chromatogram or the TLC plate with a colorless components, right? So once applied, the color component is formed. Different types of visualizing agents are used. For example, ninhydrin, right, which is important for amino acids. Remember we spoke about in UV before that if there's some type of crime scene or anything like that, right? If you touch something, amino acids are left, proteins are left around the place, and you can't see them. So you spray in hydrogen to see these different things, to color these different compounds that are not showing visible light, right? So ninhydrin is one of these visualizing agents that we tend to use in chromatography as well, right? So we can see how to calculate our retention factor up here. Really, really simple, right? If the solvent traveled to 10 and your solute is at 4, then it's 4 over 10, 0.4. Really, really simple, right? To calculate that. And you really look at it based on, you really calculate where the solute is based on the center of the dot. So you don't do it at any type of edge, you calculate from the center, right? And here we can look at this. So this is UV light we can use to find these colors, right? Or I can use P anisaldehyde, or we can use iodine, right? So these are different ways we can visualize the splitting on the chromatograms, right? Okay. So these are TLCs. That should be fine. Okay. Any questions or concerns thus far? Any issues at all? Let me know. Yes or no. Any issues? All right, no issues. Okay, should be fine enough. All right, so we're gonna continue our terminology, right? So retention time is also important. This is the time measured from the solute, from the injection of the solute needed for a solute to be eluted, right, from a chromatography column, right? So what we're saying, the retention time is the time taken for the solute to be added at the top to it actually being coming out at the bottom, right? So the time it stays in the column, that is what the retention time is. And solvent front now, this is the distance the solvent moves from the baseline. So the retention time here now would be here, right? So it's the time it stays in the entire thing, okay? While the solvent front would be where the solvent ends up, right? The distance moved from the solvent from the baseline, okay? So here are different experiments, you know? It should make sense. All right. So let's have a look at this now. Basic steps of chromatography, the procedures now, right? So let's look at this now. Column chromatography. After the column is packed, the procedure is what we tend to do now is add the mixture to be separated to the top of the column, then allow the mixture to soak into the column, right? Keep adding the solvent or the mobile phase, right, to the top of the column. Do not let the stationary phase become dry. Always keep the mobile phase there. Repeat, do not let it dry out. Don't let it run dry at all. Right? It will affect the experiment. Right? So we continuously add solvent to make sure that solvent is continuously being drained through the column. Right? Then we collect the fractions of appropriate volume in test tubes at the bottom of the column, right? So that's how we do it. So notice I'm giving you exactly how we do the procedures, right? So this is how it's done, and this is a picture of how it looks, right? Hopefully we've done this before in an experiment. Hopefully we've done this before, all right? So fractionating column, really well, not a fractionating column. Oh wow, a chromatographic column, all right? For thin layer and paper chromatography now, the procedure is the same for both TLC and paper chromatography. So we place a spot of the mixture to be separated on the baseline, right? We dip the paper or the TLC plate into the solvent, and the solvent level must be below the baseline. Please remember that. The baseline is what you draw with a pencil, and your solvent level must be below that line, right? That you place the mixture on. You allow the solvent to move up the TLC or the paper. When the solvent front is near the top, we mark its position. When carrying out the TLC or paper chromatography, please remember to mark the baseline and the solvent front with a pencil. The components of ink will be chromatographed as well, right? So if you use any type of pen, that will be chromatographed. We don't want that to happen. Remember to put a cover over the tank or beaker. This prevents solvent loss by evaporation and allows the equilibrium of the vapor, right? Well, allows the equilibration, right? The equilibration, right, or the formation and equilibrium of the vapor and the liquid solvent, right? So it keeps that equilibrium, the system in equilibrium as the solvents continue to become, well, the solutes become chromatographed, right, as they separate. So we have that there. So we always keep them in an enclosure, right, and make sure that the solvent level is below our starting line, our baseline. And then we always mark our baseline on our solvent front with a pencil. Okay. Hopefully all of it is making sense. Hopefully everything is fine. Now, stationary phases now. So usually for our column chromatography, stationary phases, right, may be solid, a gel, or liquid, right? If it is a liquid, it may be distributed on a solid. So this solid may or may not contribute to the separation process. The liquid may also be chemically bonded to the solid or immobilized onto it. So if you have a liquid stationary phase, it shouldn't be moving with your solvent. Go ahead. Raise your hand, Jordan, as well. Okay, she raised her hand, but I'm not hearing anything. All right. The expression chromatographic bed or the sorbent may be used as a general term to denote any of the different forms in which the stationary phase is used, right? So it's usually the expressions chromatographic bed or sorbent, right? Is used to denote the stationary phase. All right, so we can use that as well. So we're talking about a sorbent, we're talking about the stationary phase. If you're using chromatographic bed, we're talking about a stationary phase. All right. So stationary phase now, particularly in gas chromatography, where the
No,
stationary
sir.
phase.
I was yes, but you already answered the question.
All right, okay. So particularly in gas chromatography, where the stationary phase is most often a liquid, the term liquid phase is used for it as compared to the gas phase. All right. Examples of stationary phase is now alumina, silica gel, and cellulose tend to be used. Right. I normally use alumina. Right. So looking at the stationary phase now, right? If we use these things, looking at it in its micromolecular structure, right? Looking at the stationary phase, you can see that these intricate holes and structures exist at these levels, right? Allowing for molecules to actually move through, right? And the surface area of it is really high. So things that are molecularly the same, right, will actually stick to the stationary phase, right? While things that are not molecularly the same will actually just pass through. So that's how you look on a microscopic level. Okay, so we load the sample, right, and the sample flows through these. If the sample is closed, well, is actually going to be interacting molecularly, then it's going to be really stuck, right, within these intermolecular interactions, right? But if it's really not really going to be interacting at all, let's say that the stationary phase is non-polar and the solvent is non-polar, then it's going to be moving through fine, right? But let's say that the stationary phase is non-polar, right? um I think I should rephrase that. Let's say that the stationary phase is polar, right? And our solvent is polar, right? It's gonna be moving slower through the fractionating tower because there's gonna, well, not fractionating tower, the column, right? Because the substances themselves are gonna be really attracted, right? So they're gonna have a lot of intermolecular interactions. But if they're different, right, there's not gonna be a lot of interactions, and you're gonna have it flowing through really easily. Oh, everything is lagging here. Is that cleared up? Hmm. I don't want anything to be lagging, you know. All right, so let me just continue. So silica gel specifically is an example of stationary phase, right? So at the surface of silica gel, you have silicon to oxygen hydrogen bonds, right? Instead of silicon oxygen silicon bonds. So the surface of silica is very polar, and because of the OH groups, right, can form hydrogen bonds with suitable compounds around it, as well as van der Waals dispersion forces, and dipole-dipole interactions. So other commonly used stationary phase like alumina also have the surface OH groups attached, right? So these OH groups can really react with polar solvents, all right? So if it was non-polar now, it will move past fine. If it's polar now, then it's gonna really take a long time to actually move through. So if we're looking at this now, if we have benzyl alcohol, which is extremely polar. We're gonna have a lot of interaction with silica and the benzyl alcohol. If we have benzaldehyde, which is polar but not as polar as benzyl alcohol, we're gonna have some amount of interaction as well. If we have ethyl benzene, it is completely non-polar and will flow through without any disturbances. So please make sure that when you're speaking about your different types of stationary phase and your aqueous phases or mobile phases, right? You also look at the molecular characteristics, right, of both substances. All right. Question: are there major issues here? I'm seeing the chat. Is everything still lagging? Guys, can you hear me? Is everything still lagging? Hmm, not hearing. All right, I guess we'll just continue then. So for the mobile phase now, a fluid which percolates, right, through or along the stationary bed is defined, well, in a definite direction, right? Um, in a definite direction. It may be a liquid chromatography, or a gas chromatography, or a supercritical fluid chromatography, right? In gas chromatography, the expression carrier, right, gas, may be used for the mobile phase. In elution chromatography, the expression eluent, right, is used for the mobile phase, right? So all of this information is there. All right. So let's just stop at this checkpoint here.